Reality is built on invisible foundations. Beneath everything you see and touch, hidden fields govern the cosmos, dictating the rules of existence from the shadows. We are about to journey through 30 of the most profound theories about these unseen architects. By the end, you will understand the universe not as a collection of objects, but as a symphony of interacting, fundamental fields. We will uncover what dark energy truly might be and question if gravity is even a fundamental force at all. What hidden layer of reality most captures your curiosity? Our journey begins with the only hidden field scientists have ever directly confirmed. The Higgs field is an invisible energy ocean that fills every cubic inch of the universe. It is not made of atoms or particles in the traditional sense. Instead, it is a fundamental property of empty space itself. Think of the entire cosmos as submerged in a kind of cosmic molasses. When other particles move through this molasses, they interact with it. This interaction is what we experience as mass. A particle that interacts strongly with the Higgs field, like a top quark, becomes very heavy. A particle that interacts only weakly, like an electron, remains almost weightless, and a particle like a photon, which does not interact with the field at all, zips through the universe at the speed of light, completely massless. This process, called the Higgs mechanism, is what gives everything its substance. For decades, this was just a brilliant piece of mathematics. Then, the Large Hadron Collider at CERN went to work. Scientists there were not looking for the field itself, which is everywhere and impossible to isolate. They were hunting for its signature. Just as a splash is proof of a pebble hitting water, they sought a tiny ripple in the Higgs field. That ripple is the Higgs boson. Its monumental discovery in 2012 was not just about finding a new particle. It was our first real glimpse into the hidden architecture of reality, confirming that mass is not an innate property, but a gift from an unseen cosmic field. This single discovery cemented the final piece of the standard model of particle physics. It answered a question we hardly knew how to ask: why does anything have weight at all? The answer lies in a silent, endless field that touches every part of our existence. But if the Higgs field gives the universe its substance, what gave it its size? The cosmos we see today is staggeringly vast, yet observations reveal a deeper mystery. Its temperature is almost perfectly uniform from one end to the other. Regions of space now billions of light years apart were once close enough to exchange heat, like 2 cups of coffee evening out their warmth, but according to the standard Big Bang timeline, they were never close enough for this to happen. It is a cosmic clue that something is missing from the story. The leading solution is a hidden field known as the inflaton. This is the engine thought to have powered cosmic inflation, a breathtaking growth spurt in the universe's first fleeting moments. For a sliver of time so short it defies human comprehension, the energy of the inflaton field caused space itself to expand faster than the speed of light. It was not matter flying apart, but the very fabric of reality stretching exponentially, smoothing out the early universe into the even, flat cosmos we observe. This violent smoothing also planted the seeds for all future structure. Tiny quantum fluctuations, minuscule ripples in the inflaton field itself, were stretched to enormous sizes. These ripples became the gravitational blueprints for everything to come, the eventual galaxies and cosmic voids. Then, just as suddenly as it began, the process ended. The inflaton field decayed, its immense potential energy flooding the universe with a seething hot soup of particles and radiation. This was the moment of reheating, the true beginning of the classic Big Bang fireball. Without that brief, unimaginable stretch driven by a hidden field, our universe would likely be a small, lumpy, and barren place. The Higgs field does not act alone. It is merely the most famous resident of a far grander and more vibrant hidden reality. This brings us to the true bedrock of modern physics, a concept so powerful it redefines what a particle actually is. At its heart, every single electron in the universe is not a tiny, isolated speck. It is a tiny knot of energy, a gentle excitation in a single, universal field that stretches across all of space and time. This is the electron field, and it is not alone. There is a quark field for every type of quark, a neutrino field, and a field for the photon, the particle of light. This is the core of quantum field theory. In this view, the universe is not filled with particles, it is filled with fields. What we perceive as particles are merely the most noticeable notes in an endless, humming symphony of these fields. When you see the flash of a photon, it is the photon field vibrating at that specific point. When you feel the solidity of your desk, it is the collective dance of excitations in the electron and quark fields that make up its atoms. This framework is not just a philosophical shift, it is one of the most stunningly accurate theories humanity has ever devised. It successfully describes 3 of the 4 fundamental forces of nature. The electromagnetic force is carried by excitations in the photon field. The strong nuclear force, which glues atomic nuclei together, is mediated by particles from the gluon field. The weak nuclear force, responsible for certain types of radioactive decay, arises from the W and Z boson fields. Only gravity, for now, remains outside this elegant picture. The predictions of quantum field theory have been tested to an almost unimaginable precision, matching experimental results to more than 10 decimal places. It tells us that what we call empty space is not empty at all. It is a seething, bubbling foam of potential where fields constantly flicker with transient excitations, borrowing energy from the future to spark in and out of existence. This is the quantum vacuum, and it is alive with hidden activity, so the next time you look at a solid object, try to see it for what it truly is, a concentrated ripple in the silent, invisible fields that are the true substance of our cosmos. Yet for all its power, quantum field theory faces a monumental challenge with the most familiar force of all. You feel its pull with every step you take, yet gravity refuses to fit into this elegant framework. Our understanding of gravity comes not from the quantum world, but from a breathtakingly different picture painted by Albert Einstein. In his theory of general relativity, gravity is not a force transmitted by a particle. It is the curvature of spacetime itself. Think of the universe not as a static stage, but as a vast, flexible trampoline. A massive object like our Sun sits in the center of this fabric, creating a deep dimple. The Earth, rolling along this curved surface, is not being pulled by an invisible string. It is simply following the straightest possible path through a warped geometry. What we perceive as the force of gravity is really just the experience of moving through this bent landscape. This cosmic trampoline is the gravitational field, and every object with mass or energy contributes to its shape. This theory has passed every test thrown at it for over a century, predicting the bending of starlight around the Sun and the precise timing of the clocks on our GPS satellites. But here lies the great conflict. General relativity describes the universe on the grandest scales, the dance of galaxies, and the expansion of the cosmos. Quantum field theory describes the universe at its smallest, the frantic world of atoms and particles. Each is spectacularly successful in its own domain, but they are fundamentally incompatible. When we try to describe the gravitational field using the rules of quantum mechanics, the mathematics breaks down into nonsense, producing infinite probabilities. This tells us our picture is incomplete. The search for a quantum theory of gravity, for a hypothetical particle called the graviton that would be an excitation of a gravitational field, is one of the greatest quests in modern physics. It is a search for the missing note that would complete the universe's symphony, finally weaving gravity into the tapestry of quantum fields. This great conflict between gravity and the quantum world is not the only crack in our understanding. Deep within the equations describing the strong nuclear force, the very glue that holds atomic nuclei together, lies another subtle but profound mystery. It is known as the strong CP problem, and its solution might require another hidden field, one that could also be the very substance of dark matter. The strong force, governed by quantum chromodynamics, has a peculiar feature. Its equations allow for a certain kind of asymmetry, a difference in how it treats particles and their mirror images, combined with a reversal of their charges. This asymmetry, if it were present, would leave a distinct electric dipole moment on the neutron, a tiny separation of positive and negative charge within this neutral particle. Yet, no experiment has ever detected it. The neutron's symmetry is perfect to an astonishing degree, as if a fundamental dial in the universe's settings has been tuned to zero with inexplicable precision. Why is nature so symmetric when our best theories suggest it should not be? This is the strong CP problem. To resolve this, physicists proposed a new field, and with it, a new particle, the action. The action field is thought to permeate all of space, acting like a cosmic lubricant that naturally cancels out this unwanted asymmetry, smoothly rotating the dial to zero and restoring the perfect symmetry we observe. It is an elegant fix, but it came with a stunning consequence. The action, the ripple in this field, would be incredibly light and incredibly slow-moving, a ghostly particle that barely interacts with ordinary matter. This makes it a perfect candidate for the mysterious dark matter that holds galaxies together. We could be swimming in an ocean of actions, a coherent field so diffuse we never feel its individual particles, yet whose collective gravity shapes the cosmos. The hunt for this ghost is on. Experiments use powerful magnetic fields to try and coax an action into revealing itself by converting into a faint photon, a whisper of light in a dark chamber. Others look for subtle distortions in the light from distant neutron stars. Finding the action would be a monumental double discovery, solving one of particle physics's most stubborn puzzles while simultaneously illuminating the nature of most of the matter in the universe. But the action is not the only ghost in the machine. Another hypothetical field offers an even more radical solution to the greatest puzzle in modern cosmology, the mystery of dark energy. This is the chameleon field, a concept as clever and elusive as its name suggests. It is a scalar field, a cousin to the Higgs field, but with a bizarre and unique property. Its mass and the strength with which it interacts with matter are not fixed, they change. In environments dense with matter, like here on Earth or within our solar system, the chameleon field becomes incredibly heavy and short-ranged. It effectively hides, its influence shrinking to a scale so small it becomes virtually impossible to detect with our most sensitive instruments. It blends into the background, a master of disguise. Yet, in the near-perfect vacuum of interstellar space, the field undergoes a dramatic transformation. Its mass drops precipitously, and its range expands to cosmic proportions. In this state, the chameleon field can exert a gentle, repulsive pressure on the very fabric of space. This is the ingenious twist. The field's behavior is not set by some universal constant, but by its local environment. It explains why we do not feel its effects nearby, and why it only manifests its power in the emptiest reaches of the cosmos, precisely where we observe the universe's expansion accelerating. Detecting this cosmic chameleon is a monumental challenge. Laboratory experiments must be designed to create an ultra-low-density vacuum within a small chamber, a tiny pocket of emptiness where the field might become light enough to reveal its presence. Scientists look for subtle forces or shifts in energy levels that could betray an interaction with this hidden field. The quest is to catch it in the act of changing its skin, to prove that the energy driving the cosmos apart is not a static force, but a dynamic, shape-shifting field that has been hiding in plain sight all along. Another shape-shifting field proposed by theorists is the symmetron. Like the chameleon, the symmetron's influence depends entirely on its surroundings, but its mechanism is a story of cosmic symmetry. Imagine a pencil perfectly balanced on its tip. In that precarious state, it is completely symmetric, pointing in no particular direction, but the slightest vibration will cause it to fall, choosing one specific direction and breaking that perfect symmetry. The symmetron field operates on a similar principle. In regions of high density, where the average mass is great, the field remains in a symmetric state. Its value is zero, and it effectively switches itself off, having no noticeable effect on gravity. In these crowded cosmic neighborhoods, Einstein's general relativity reigns supreme, completely undisturbed. But in the vast, empty voids between galaxies, where the average density of matter drops below a critical threshold, something remarkable happens. The symmetron field undergoes a spontaneous phase transition. Like that pencil finally falling, it picks a specific value, breaking its symmetry. In this activated state, the field begins to exert a new, repulsive force. It effectively modifies gravity, causing a gentle push that contributes to the accelerated expansion of the universe. This offers an elegant explanation for dark energy. It is not a mysterious constant, but the dynamic effect of a field that only turns on where the universe is most empty. The challenge, of course, is catching it in the act. Scientists are designing experiments sensitive enough to detect the incredibly faint forces a symmetron would produce. One approach involves measuring the precise motion of atoms in an ultra-high vacuum chamber, a tiny human-made void where the symmetron might subtly reveal its presence. Another looks for telltale distortions in the orbits of stars within galaxies, seeking signs of a fifth force that fades in and out of existence. The symmetron represents a beautiful idea that the laws of physics themselves might not be fixed, but could change depending on where you are in the cosmos. The symmetron suggests the laws of physics might be local, but the dilaton proposes they could have been fluid in time. This journey takes us into the heart of string theory, a framework where the fundamental ingredients of reality are not point-like particles, but unimaginably tiny, vibrating strings. The character of each string's vibration determines whether it manifests as an electron, a quark, or a photon. But for this symphony of strings to produce the universe we know, it requires a conductor. That conductor is the dilaton field. This scalar field is woven into the very fabric of the string theory landscape, and it governs a profound aspect of reality, the overall strength with which all particles interact. Think of it as a universal volume knob for the forces of nature. The intensity of the electromagnetic force, the power of the strong nuclear force, even the gravitational constant itself, could all be tied to the value of this single, all-pervasive field. In the most straightforward versions of the theory, the dilaton has a crucial job, helping to compactify the extra dimensions that string theory requires. We perceive only 3 dimensions of space and 1 of time, but the theory suggests there are more, curled up into shapes so small we cannot detect them. The dilaton field helps stabilize these hidden dimensions, determining their size and shape, which in turn sets the values of the constants we measure in our 4-dimensional world. But what if that value was not always the same? A dynamic dilaton field in the very early universe would mean the constants of nature were not constant at all. The fine structure constant, which dictates the strength of electromagnetism and the very possibility of chemistry and life, could have been slowly shifting. This is not just a wild speculation. Scientists have looked for evidence of this by studying the light from incredibly distant quasars, ancient beacons whose light has traveled for billions of years. They analyze the absorption lines from ancient gas clouds, searching for minuscule differences in the perceived strength of electromagnetism in the distant past. While the evidence remains controversial, the possibility is staggering. It suggests a cosmos where the very rules of the game were still settling into place, a universe conducted by a field whose silent tuning made our existence possible. The dilaton hints that nature's constants might evolve, but quintessence takes this idea to the very edge of cosmic fate. This theory proposes that dark energy is not a static feature of empty space, but a dynamic, evolving field. Its name is a deliberate echo of the ancient philosopher's fifth element, the pure substance of the heavens. Unlike the cosmological constant, which is a fixed, immutable energy density forever driving the universe apart, quintessence is alive. It is a scalar field, much like the Higgs, but one that is slowly rolling down a gentle slope of potential energy. The energy density of this field is not constant. As it rolls, its pressure becomes negative and repulsive, acting as an accelerating force on the cosmos. The key difference lies in its evolution. In some models, the field's roll is slowing, meaning its repulsive power could weaken over billions of years. In others, it could eventually reverse, turning attractive. This simple change completely rewrites the universe's final chapter. A cosmological constant leads to a forever expanding, cold, and empty cosmos, a relentless acceleration tearing all structure apart in a big rip. But quintessence offers alternative endings. Perhaps the acceleration is a temporary phase, a cosmic sigh before the universe settles into a more gentle expansion. Or, in a more dramatic turn, the field could decay entirely, its energy transforming into new particles and radiation, leading to a cyclical universe or even a future collapse. The evidence for this lies in the subtle details of the expansion itself. Astronomers meticulously measure the expansion rate at different cosmic epochs, searching for any sign that the strength of dark energy has changed over time. Is the push getting stronger, or is it fading? The answer is written in the distribution of galaxies and the dimming of distant supernova. Finding a dynamic field behind dark energy would be a revolution, revealing a cosmos not governed by a simple number, but by a living, breathing entity whose slow dance dictates our ultimate destiny. Einstein's vision of spacetime as a smooth fabric is not the end of the story. That cosmic trampoline might not just bend, it could also twist. This is the realm of torsion, a hidden property of geometry that general relativity famously ignores. In Einstein's original theory, the curvature of spacetime is produced by the energy and momentum of matter. But what about the intrinsic spin of particles, that tiny quantum rotation every electron and quark possesses? The Einstein-Cartan theory weaves this spin directly into the fabric of gravity. It proposes that spacetime itself can carry a kind of twisting, a torsion generated by the microscopic spins of the particles within it. Think of the difference between bending a flexible rod and twisting it. General relativity describes the bend, while torsion describes the twist in the very threads of reality. This is not a violent, large-scale writhing, but a subtle, microscopic corkscrewing of the geometry at the very smallest scales. The presence of this torsion field introduces a cosmic repulsion that becomes significant only under the most extreme densities. And this has a breathtaking consequence for the ultimate cosmic endpoints. In the standard story, a massive star collapsing into a black hole is crushed by its own gravity into an infinitely dense point, a singularity where the laws of physics break down. But with torsion, the story changes. As matter is compressed towards that point, the collective spin of all the particles generates such a powerful torsional repulsion that it counteracts the crush of gravity. The collapse does not end in a point of infinite density. Instead, the matter rebounds like a cosmic spring. The black hole's heart could become a bridge to another region of spacetime, a wormhole, or even a new universe budding off from our own. Torsion offers a way to heal the most troubling wounds in our understanding of gravity, suggesting that nature, in its infinite cleverness, uses every property of matter, even its spin, to prevent its own laws from breaking. Spacetime can ripple, and we have felt its waves. The detection of gravitational waves was a monumental leap, not just confirming a prediction of Einstein's relativity, but opening a new window onto the cosmos. These waves are literally vibrations in the fabric of spacetime itself, stretching and squeezing everything in their path as they travel at the speed of light. But what creates these ripples? They are generated by the most violent events in the universe, the collisions of black holes and neutron stars. Yet, to truly understand gravity at its most fundamental level, we must ask what carries this force. In the quantum world, every force has a messenger particle. For electromagnetism, it is the photon. For the strong force, it is the gluon. Gravity, if it is to be united with the other forces, must have its own quantum carrier, a hypothetical particle known as the graviton. The graviton would be a tiny ripple in its own universal field, the gravitational field. This is the graviton field, the proposed quantum foundation of gravity. It would be a tensor field, more complex than the scalar Higgs field, describing not just a value at each point in space, but a direction and a stress, a full description of spacetime's geometry at the quantum scale. The challenge of quantizing gravity is immense. When physicists try to apply the rules of quantum field theory to the graviton, the mathematics often produces infinities that cannot be renormalized or smoothed away as they can with the other forces. The problem is that gravity is the curvature of spacetime itself, and the graviton is the particle that would be responsible for that curvature. You end up with a self-referential puzzle, a particle that defines the stage upon which it is supposed to perform. This is why detecting gravitational waves was so crucial. While these waves are a classical phenomenon, described perfectly by Einstein's equations, they are also a direct probe of the gravitational field. Studying them is like studying ocean waves to understand the property of water. Each wave carries information about the source that created it, and by analyzing their patterns with instruments like LIGO and Virgo, we are essentially testing the behavior of the gravitational field in its most dynamic state. We are not yet detecting individual gravitons, but we are learning to read the handwriting of the field from which they must emerge. The quiet chirp of a colliding black hole, translated from a faint spacetime vibration into a sound we can hear, is a message from the deep structure of reality, a clue in our long quest to hear the quantum whisper of the graviton. Time itself might not be the continuous flow we perceive. Some theories propose that time is granular, composed of the smallest possible ticks, indivisible moments known as chronons. This idea springs from the chronon field, a hypothetical structure that would quantize the very progression of time. Just as a digital movie is made of discrete frames, our experience of a flowing present could be the macroscopic result of these fundamental time atoms flashing by. The scale of this quantization is almost incomprehensibly tiny, believed to be the Planck time, a duration of about 10 to the minus 43 seconds. At this level, the smooth trajectory of a particle through space would be replaced by a flickering sequence of positions like a cosmic flipbook. The implications for physics are profound. The notorious infinities that plague quantum gravity might simply vanish, smoothed away by the discrete nature of the underlying spacetime fabric. Paradoxes like the information loss in black holes could find new resolutions, as information would have a finite number of time steps to be processed or encoded. Even the nature of free will and consciousness is touched by this idea. Does a decision unfold across a continuous span, or is it the result of a single, decisive tick in the chronon field? We have no experimental proof for this yet, as detecting such a brief interval lies far beyond our current technology, but the concept challenges our most basic intuition, suggesting that the river of time is not a river at all, but a cascade of fundamental moments, a hidden clock ticking at the heart of all existence. If time itself is granular, what then of the events that unfold within it? A more radical proposal suggests that information is not just a record of reality, but its very substance. This is the theory of the information field, the idea that every particle, every force, and every moment is fundamentally a packet of data. In this view, the universe does not merely contain information, it is information. The bits and bytes are not abstract concepts, they are the physical bedrock of existence, perhaps even woven into a universal field that dictates what is possible and what is real. The most stunning evidence for this comes from a principle born from the study of black holes, the holographic principle. When an object falls into a black hole, a profound question arises. What happens to all the information that described that object, the precise arrangement of every single atom? The laws of quantum mechanics insist that information can never be truly destroyed. The holographic principle provides a breathtaking answer. It proposes that all the information needed to describe the entire three-dimensional volume of a region of space is not stored within that volume at all. Instead, it is perfectly encoded like a cosmic hologram on the two-dimensional boundary that surrounds it. For a black hole, this is its event horizon, the point of no return. The information about everything that has ever fallen in is painted onto this spherical surface. This is not just a quirk of black holes. The principle suggests that our entire universe, in all its vast, three-dimensional glory, might be a projection from a hidden, two-dimensional information field residing at the cosmic horizon. You, the screen you're watching this on, the very air you breathe, would not be fundamentally solid objects, but a magnificent translation of data from a distant, flat surface. It is as if the reality we experience is an incredibly detailed and immersive movie, but the master copy of the film is stored on a simple, two-dimensional disk at the edge of everything. This transforms our understanding of space and matter. The solidity of your hand is an illusion of density, a rich and complex region of the projection. The flow of time could be the sequential reading of this cosmic data, the search for the pixels of this universal display, the individual bits of the information field, is one of the most profound quests in physics, aiming to prove that we are not just made of atoms, but of immutable cosmic truths. Perhaps the most intuitive challenge to the quantum mystery comes from a forgotten path. While the Copenhagen interpretation tells us particles are ghostly probability waves until observed, an alternative vision insists they are always real, guided by an unseen hand. This is the pilot wave theory, a deterministic universe hiding beneath the veil of quantum weirdness. In this picture, every particle has a definite position and path at all times. It is never a smeared-out wave of possibility, but how then does it produce the strange interference patterns of the double-slit experiment, where a single electron seems to pass through both slits at once? The answer is a hidden field, a guiding wave that fills all of space. This quantum potential field does not push or pull the particle with a force like gravity. Instead, it acts as an information field, a cosmic map that informs the particle of its entire environment. The particle rides this wave like a surfer on a complex, evolving swell. The wave itself passes through both slits, interfering with itself to create a pattern of peaks and troughs. The surfer, the actual particle, is then guided along one specific channel in this pattern, never deviating from a single, definite path. Yet, when you repeat the experiment with many particles, each one guided by the same undulating wave, they naturally build up the classic interference stripes. The bizarre behavior is not in the particle, but in the intelligence of the guiding field. This pilot wave is a non-local field, meaning its shape is instantly informed by conditions everywhere. A change in one part of the experiment immediately alters the entire wave, and thus the path of the particle, no matter how far away. This restores a concrete reality to the quantum world, but at the cost of a mysterious, instantaneous connection woven into the fabric of space. The theory can reproduce all the strange phenomena of standard quantum mechanics, from quantum tunneling to entanglement, but it paints a radically different picture of what is actually happening. We are not living in a world of chance, but one of intricate, predetermined choreography, where every particle dances to the silent tune of a hidden field. The quantum vacuum is anything but empty. Beneath the illusion of stillness lies a seething ocean of raw potential, a fundamental hum of activity that never ceases. This is the zero-point field, the lowest possible energy state that a quantum field can possess. According to the rules of quantum mechanics, a field can never truly be turned off. It constantly fluctuates, borrowing energy from the future to spark with transient pairs of virtual particles and antiparticles. They flicker into existence for the briefest of moments, only to annihilate each other and return their energy loan, a frantic dance of creation and destruction happening in every single cubic centimeter of space. The energy density of this field is mathematically staggering. If you could somehow extract the zero-point energy from a single coffee mug of empty space, the calculations suggest it would contain more energy than all the visible matter in the entire universe. This is not a gentle background hum, but a roaring hurricane of power locked within the fabric of reality itself. We even have direct experimental proof of its existence. The Casimir effect demonstrates this hidden activity with elegant simplicity. Imagine two uncharged, perfectly smooth metal plates placed incredibly close together in a vacuum. The empty space between the plates restricts the kinds of quantum fluctuations that can occur there, while the space outside the plates remains rich with a wider spectrum of this activity. This imbalance creates a subtle pressure, pushing the plates together. It is not a mysterious force, but the gentle, measurable push of the zero-point field itself, a whisper from the quantum void proving it is real. Yet this confirmation leads directly to one of the most vexing problems in all of physics. When we try to calculate the total energy density of this zero-point field to understand its contribution to the cosmos, we get a number that is wrong by a factor of 1 followed by 120 zeros. This is the cosmological constant problem. This calculated energy should be causing the universe to expand at a rate that would tear atoms apart before they could even form. Yet our universe is stable, its expansion gentle enough for galaxies, stars, and life to exist. So where did all that immense zero-point energy go? Why does its gravitational effect seem to vanish, leaving behind only the faint, mysterious signal we call dark energy? The zero-point field is real, its power is undeniable, but its true role in the cosmos remains one of nature's most profound and unsettling secrets. The vacuum's restless energy is profound, but what if some fields are not bound by the speed of light at all? This brings us to one of the most speculative ideas in physics, the tachyon field. Tachyons are purely hypothetical particles defined by a single, bizarre property. They are born moving faster than light and can never slow down to the speeds we consider normal. Their existence would require a complete rewrite of our understanding of causality, the law that cause must precede effect. The mathematics behind them is just as strange. In our familiar world, a particle's mass is a positive number. For a tachyon, the mass squared is a negative number, which implies the mass itself is an imaginary quantity, a concept that seems to belong to pure mathematics, not the physical world. This imaginary mass is not a flaw in the theory, but the very feature that would allow such a particle to perpetually exceed light speed. It is not accelerating through a barrier, it simply exists on the other side of it. The tachyon is not a particle speeding up, but an excitation in a tachyon field that is inherently unstable. Think of a pencil balanced perfectly on its tip. That precarious state represents the field's highest energy point. The slightest nudge, a quantum fluctuation, would cause it to fall, rolling down to a stable, lower energy state. This is the process of spontaneous symmetry breaking, and a tachyon field is thought to be the agent of such a dramatic transition in the universe's infancy. Its instability would not be a flaw, but a cosmic trigger. The moment this field collapsed from its high-energy, symmetric state into a stable, broken symmetry state, it could have released an enormous burst of energy, potentially powering events like cosmic inflation or triggering the phase transitions that gave the fundamental forces their distinct identities. While no tachyon has ever been detected, and their existence would challenge the very core of relativity, they remain a fascinating mathematical possibility, a ghost in the equations hinting that the early universe's most pivotal moments were driven by fields falling into a more comfortable shape. Beyond the quantum foam and cosmic fields lies a hypothesis that challenges the very definition of a field itself. Rupert Sheldrake's concept of the morphic field ventures into a realm that is both fascinating and fiercely debated. This is not a field of force or energy in the traditional physical sense. Instead, Sheldrake proposes a non-physical field that acts as a kind of formative blueprint, guiding the shape and behavior of living things and even the structure of crystals. It is a field of habit, of memory, a repository for the collective patterns of nature. The engine of this idea is morphic resonance, the process by which these patterns become established. Imagine a new crystal form being synthesized for the very first time in a laboratory. Initially, it might be difficult to grow, its structure unstable. But as more labs around the world succeed in creating it, the process seems to become easier. According to this theory, it is not just that chemists are getting better at the technique. The crystal itself is tapping into a morphic field that has been strengthened by all previous formations of that same crystal. The pattern, once set, resonates across space and time, making it easier for subsequent systems to fall into the same shape. This principle is extended to the biological world. It suggests that a rat in a maze in London does not just learn from its own trial and error. Its successful path somehow makes it easier for a rat of the same breed in a maze in Tokyo to learn the route faster, not through any known physical connection, but through resonance with a collective learning field established by its species. This, Sheldrake argues, could explain why certain behaviors seem to spread rapidly through animal populations without direct contact. The scientific criticism of this idea is substantial and centers on its testability. Mainstream science argues that the morphic field, as described, lacks a proposed physical mechanism. How does this information travel? How is it stored? Critics point out that many of the cited phenomena, like the increasing ease of crystal formation, can be explained by more conventional factors, such as the subtle spread of techniques or impurities in reagents. The very foundation of the hypothesis, its non-physical nature, places it outside the current framework of testable, repeatable experimentation that defines the scientific method. For many, it remains an intriguing metaphor for the mysteries of life and form. For others, it is a step too far into the unverifiable, yet it forces a profound question. Could the universe contain fields of information that we have not yet learned to measure, patterns woven not from energy, but from the silent accumulation of habit itself? Leaving behind the world of physics, we enter a realm where consciousness itself may be woven into the cosmos. The Akashic field is a concept that bridges ancient mysticism and modern speculation, proposing a non-physical library of everything that ever was. In theosophical tradition, the Akashic records are described as an ethereal imprint, a cosmic memory that holds every thought, word, and event that has ever occurred. It is not a field of force, but a field of information, the universe's own perfect and eternal archive. Some modern theorists, grappling with the hard problem of consciousness, have attempted to find a scientific foothold for this idea. They ask if this Akashic record could be physically embedded within the quantum vacuum, the same seething zero-point field we now know is real. Could the frothing sea of virtual particles and energy fluctuations be more than just random noise? Could it be a medium for storing and transmitting information on a cosmic scale, a physical substrate for what mystics have called the Akasha? The connection is profoundly speculative, yet undeniably compelling. It suggests that our individual consciousness might not be locked inside our skulls, but could be a localized reading of this universal information field, like a radio tuning into a specific station from a vast broadcast. Every experience you have, every memory you form, might not just be a pattern of neural connections, but a unique entry into this cosmic ledger. The challenge, of course, is that this remains entirely outside the scope of testable science. There is no instrument that can measure a thought from the past, no experiment to verify if the vacuum holds memories. For critics, it is an untestable hypothesis, a beautiful story without empirical foundation. Yet it forces a staggering question about the nature of reality itself. Is the universe not just made of matter and energy, but of meaning? Are the fields we have been exploring not just the architects of physical form, but the scribes of history? The Akashic field, whether metaphor or reality, points toward a cosmos that is not just alive, but awake and perhaps remembering. A single equation might one day describe the entire cosmos. This is the dream of a unified field theory, the ultimate quest to show that all of nature's forces and particles are just different melodies played on one fundamental instrument. For centuries, we have watched these forces appear to act independently. Gravity shapes the universe, electromagnetism binds atoms, and the nuclear forces govern the hearts of stars. Yet physicists suspect this separateness is an illusion, a consequence of the universe cooling from a more symmetric, primordial state. The first major step in this grand synthesis are grand unified theories, or GUT. These theories propose that at energies so high they are almost unimaginable, like those present a fraction of a second after the Big Bang, the electromagnetic force and the weak and strong nuclear forces were not three distinct forces at all. They were one single unified interaction. Think of water. At high temperatures, it is a uniform vapor, but as it cools, it can condense into liquid or freeze into solid ice. These are different phases of the same substance. In a similar way, as the universe expanded and cooled, this single unified force is thought to have undergone a series of phase transitions, crystallizing out into the three distinct forces we recognize today. This beautiful idea makes a dramatic prediction. It suggests that the proton, the very heart of every atom, might not be perfectly stable. It could decay, vanishing into a burst of energy after an immense timescale. Giant experiments deep underground, filled with ultra-pure water, have been waiting for a single proton to disintegrate within their vast tanks. So far, none have been seen, telling us that if protons do decay, their lifetime is far longer than many simple GUTs predicted. This is a clue that the ultimate theory must be even more intricate. the quest for unity pushes beyond GOTs into the realm of strings. Superstring theory makes a breathtaking leap. It proposes that the fundamental entities of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrational patterns of these strings are what manifest as electrons, quarks, photons, and gravitons. In this framework, every particle and every force emerges from the music of these strings. The theory naturally includes gravity, weaving the graviton into the same tapestry as the other forces. But to make the mathematics work, string theory requires more dimensions than the 3 of space and 1 of time we experience. It suggests the universe has 6 or 7 extra spatial dimensions, all curled up into shapes so small that we are oblivious to them. The specific geometry of these hidden dimensions would determine the properties of our 4-dimensional world, setting the values of constants like the charge of the electron. This leads to M-theory, a broader framework that unites the different versions of string theory, hinting that they are all glimpses of a single, deeper truth. The challenge is immense. The energy scales required to probe these tiny strings or uncurl the extra dimensions are far beyond the reach of any particle accelerator we could ever build. The theory currently predicts a vast landscape of possible universes, each with different physical laws, leaving us to wonder why we inhabit this one. Yet the pursuit continues, driven by the profound belief that the universe is not a collection of separate parts, but an elegant, unified whole, waiting for us to decipher its deepest, most beautiful secret. The strange rules of the quantum world are not confined to the microscopic. Under the right conditions, they can swell to fill a room, creating a new state of matter where the very idea of individual particles vanishes. This is the realm of Bose-Einstein condensates, when a cloud of certain atoms is cooled to a fraction of a degree above absolute zero, a bizarre transformation occurs. The atoms lose their individual identities, their distinct quantum wave functions merging into one single, giant wave function. They begin to behave as a single, coherent superatom, a macroscopic entity governed by quantum law. In this state, the quantum field that describes these particles is no longer a buzzing hive of separate excitations. It has undergone a phase transition, condensing into a unified, classical-like wave that you can almost see and touch. This is a condensate field made visible, a hidden quantum reality blossoming into our everyday world. The implications ripple out from the lab to the cosmos itself. Could dark matter, the invisible glue of galaxies, be a form of cosmic condensate? Perhaps it is not made of discrete, weakly interacting particles, but is instead a pervasive, ultra-low energy field that has condensed across the universe. This would explain why it does not clump densely like ordinary matter, but forms a smooth, massive halo around galaxies, its wave-like nature preventing it from collapsing into bright, dense stars. The principle reaches back to the very beginning. The inflatoned field, thought to power the universe's explosive birth, might have behaved like a condensate. In that primordial fireball, it could have been a single, coherent field whose uniform energy drove the rapid stretching of space, its eventual decay into particles marking the end of inflation and the start of the hot Big Bang. When countless particles march in perfect quantum lockstep, they reveal a hidden layer of reality where the field itself becomes the object, a silent, coordinated dance on the grandest of stages. Phantom energy is a nightmare version of dark energy, a field whose repulsive power does not fade but grows stronger over time, while the cosmological constant is a steady push and quintessence might ebb and flow. Phantom energy is an ever-intensifying scream. Its terrifying nature is defined by a single number, its equation of state. For phantom energy, this value is less than -1, a mathematical condition that translates to a physical reality of runaway expansion. Imagine the universe's expansion today, gently pulling galaxies apart. With phantom energy, that gentle pull becomes a relentless tug, then a violent yank. The acceleration would not just continue, it would increase exponentially. The first casualties would be the largest structures, galaxy clusters, bound by gravity for billions of years, would be shredded. Their member galaxies would be flung into the ever-widening emptiness. Then, gravity would lose its grip on individual galaxies, the Milky Way would be torn asunder, its stars scattered like cosmic dust. As the end draws nearer, the destructive force invades every system. A few 100 million years before the final moment, our own solar system would be ripped apart. The Sun's gravity would no longer be enough to hold the planets in orbit. Earth would be flung into the freezing, dark void. In the last hour, the horror becomes personal. The phantom field's repulsive force would overcome the electromagnetic force holding our planet together. Earth itself would explode. Minutes later, the same fate would meet the Sun and every other star. In the final, fleeting instants, atoms themselves would be torn apart as the forces binding nuclei and electrons are overwhelmed. Molecules, cells, and the very fabric of matter would be vaporized. And at the final instant, the phantom energy field would achieve its ultimate, terrifying victory. The repulsive force would become infinite, overwhelming the very bonds of spacetime. The fabric of reality itself would be torn apart, ending the universe not with a slow fade, but with a catastrophic, fundamental rupture. This Big Rip scenario is a stark reminder that the cosmos is not necessarily a stable, permanent home. The same field that might explain the universe's accelerating expansion could, in its most extreme form, contain the seeds of its absolute and utter annihilation. Dark matter might not be a featureless, directionless substance. We have been exploring it as if it were a cosmic fluid, a scalar field with a value but no inherent direction. Yet the universe loves variety, and the next possibility is a field with an arrow attached. This is vector field dark matter. Unlike the scalar fields we have discussed, a vector field assigns both a magnitude and a specific direction to every point in space. Imagine it not as a uniform ocean, but as a vast, cosmic weather map, with gentle currents and flows streaming through the void. These currents would be the excitations of the vector field, and their collective presence would constitute the dark matter halo enveloping our galaxy. This directional quality introduces new behaviors. The field could spin, creating vortices, or it could exhibit rich wave-like dynamics that a simple scalar field cannot. One particularly compelling version of this idea is known as fuzzy dark matter. In this model, the vector field is made of particles so incredibly light that their quantum wave nature becomes important on a galactic scale. A single particle could have a wavelength as large as a dwarf galaxy. This changes everything for the small-scale structure of the cosmos. The standard model of cold dark matter, while brilliant at predicting the large-scale cosmic web, faces puzzles on smaller scales. It predicts hundreds of small satellite galaxies swarming around large galaxies like our Milky Way, but we observe far fewer. It also suggests that the dense centers of dark matter halos should be extremely cuspy and sharp, yet observations of the motions of stars within galaxies often suggest softer, fluffier cores. Fuzzy dark matter, with its wave-like essence, provides a natural solution. These galaxy-sized waves have a characteristic length. They cannot be squeezed into a volume smaller than their wavelength, which creates a natural pressure that prevents dark matter from collapsing into overly dense, cuspy centers. This results in the soft cores we seem to observe. Furthermore, the interference patterns of these vast waves would naturally suppress the formation of the very smallest dark matter clumps, neatly explaining the missing satellite problem. The dark matter halo of a galaxy would not be a static cloud. but a vibrant, waving entity, a coherent quantum field on a truly astronomical scale. We would be living inside a gentle, oscillating pattern of invisible matter, its rhythmic ebb and flow subtly guiding the architecture of the stars we see. A cosmic chameleon hides its effects near matter, but what if the mechanism is not a change in mass, but a change in influence? This is the promise of the Galilean field, a class of theories that modify gravity in a particularly clever way. Named for their mathematical symmetry under Galilean transformations, the same principle that underpins much of classical mechanics, these fields can produce a powerful cosmic repulsion. Yet they possess a built-in cloaking device, a phenomenon known as Weinstein screening, which perfectly explains why we do not see their effects in our own solar system. Imagine shouting in a crowded, noisy room. Your voice is lost in the din, having little effect on anyone beyond your immediate vicinity, but if you step out into a vast, silent plain, that same shout can carry for miles. The Galilean field operates on a similar principle. In regions of high matter density, like our solar system, the gravitational field of the Sun and planets creates an intense background noise. The Galilean field senses this dense environment and automatically suppresses its own force. Its influence becomes incredibly short-ranged, effectively screened by the presence of all the ordinary matter. This ensures that Einstein's general relativity remains unchallenged in the places we have tested it most precisely. The orbits of planets, the bending of starlight, all proceed exactly as we have observed for centuries, with no mysterious fifth force to complicate the elegant equations. But venture out into the cosmic voids, the immense and nearly empty spaces between galaxy clusters. Here, the background matter density plummets, the screening effect shuts off. In this cosmic quiet, the Galilean field's true nature is unleashed. It can exert a long-range, repulsive force that adds to the expansion of the universe, potentially driving the acceleration we attribute to dark energy. The field itself is not changing, but its interaction with the environment is. This screening is so effective that even the Earth's own gravitational field is enough to suppress the Galilean's influence in our immediate vicinity. Any modifications to gravity it produces would be utterly negligible here, hiding it perfectly from local experiments. The hunt for this hidden actor therefore focuses on the largest scales and the most delicate measurements. Astronomers look for subtle imprints in the cosmic microwave background, the faint afterglow of the Big Bang. They study the rate at which colossal clusters of galaxies form, searching for a signature that gravity behaves just slightly differently on these immense scales than general relativity would predict alone. The Galilean field represents a sophisticated attempt to have it both ways, to modify gravity for the cosmos without breaking the physics of our local neighborhood. It suggests that the force shaping the universe's fate is not absent from our solar system, but is merely waiting in the shadows, silenced by the presence of our own world. The Galilean field is a master of disguise, but it is only one actor in a much larger play. The true stage for these cosmic shapeshifters is the Horndeski field, the most general possible form a scalar field can take while still playing by the rules of gravity as we know them. This is not a single theory, but a vast landscape of possibilities, a comprehensive mathematical framework that encompasses nearly every viable model of modified gravity and dynamic dark energy. Discovered by physicist Gregory Horndeski in the 1970s, this theory was largely forgotten for decades before being rediscovered by cosmologists desperate for new tools. Its power lies in a specific constraint. The equations that describe how gravity and a field interact can easily spiral into a mathematical nightmare, producing solutions that include ghostly instabilities or violate causality. Horndeski's genius was to find the broadest possible form of a scalar tensor theory that still results in second-order equations of motion, In simple terms, this means the physics remains well-behaved and predictable without the paradoxical and unphysical behavior that plagues less carefully constructed theories. Within this single sprawling framework, you can find the chameleon, the symmetron, the Galilean, and quintessence. They are all special cases, specific paths through the immense terrain of the Horndeski landscape. This gives physicists a powerful toolkit. Instead of testing one dark energy model at a time against the data, they can test them all at once. They can write down the general Horndeski equations and then use astronomical observations to measure its parameters, effectively asking the universe to tell us which path through the landscape it actually took. The data comes from everywhere: the precise timing of cosmic clocks, the subtle distortions of light from distant galaxies due to weak gravitational lensing, the detailed map of the cosmic microwave background, and the large-scale distribution of galaxies all place constraints on this framework. Each observation acts like a surveyor's stake, narrowing down the possible territory. So far, the universe seems to be pointing toward a surprisingly simple corner of the Horndeski landscape, one where the field's effects are very subtle, closely mimicking a simple cosmological constant. Yet the door is not closed. The hunt for any deviation, any tiny crack in the foundation of Einstein's gravity, continues with ever more precise telescopes and surveys. The Horndeski field represents our best map of the unknown, a guide for exploring the hidden architecture of the cosmos without getting lost in the infinite possibilities of what might be. Every field we have met so far has a hidden twin, a more complex and fundamental actor that forms the very bedrock of matter. This is the spinor field, the mathematical engine behind every electron and quark in existence. Unlike the scalar fields that have a simple value at each point, or vector fields that point in a direction, spinor fields are something else entirely. They are mathematical objects that require a full 720-degree rotation to return to their original state, not the 360 degrees we are used to in our daily lives. This bizarre property is not a mathematical curiosity. It is the direct signature of a half-integer spin. Particles in our universe are divided into two great families, the bosons, which carry forces and have integer spins like 0 or 1, and the fermions, the building blocks of matter, with half-integer spins like 1/2. It is this half unit of spin that makes you solid. When you try to push two electrons too close together, their spinor fields interact in a way that creates a powerful repulsion. This is the Pauli exclusion principle in action, the quantum rule that prevents matter from collapsing in on itself. Without this fundamental resistance encoded in the spinor field, atoms would not have stable shells, chemistry would be impossible, and the universe would be a formless, dense soup. The spinor field is the ultimate guarantor of structure, the reason you do not fall through the floor. Its excitations are the fermions themselves, the ultimate indivisible particles that have no internal structure. When you see an electron, you are seeing a localized knot of excitation in the universal electron spinor field. The mathematics of these fields is so profound that it predicted the existence of antimatter before it was ever discovered. The equations demanded a perfect mirror for every particle, a twin with opposite charge but identical mass. The discovery of the positron, the electron's antimatter counterpart, was a stunning validation that we were reading the universe's deep code correctly. So the next time you feel the solidity of your own hand, remember that you are feeling the collective resistance of countless spinor fields, a fundamental node that gives the cosmos its shape and makes our material world possible. Mass can be given without a cosmic molasses. An alternative path to mass exists, a clever mathematical trick known as the Stuckelberg field. While the Higgs mechanism is famous for giving mass to particles like the W and Z bosons, the Stuckelberg approach provides a different, and in some ways simpler, way to give mass to a specific type of force carrier. It works for abelian gauge bosons, particles like the hypothetical dark photon that are akin to the photon but with mass. The central problem it solves is one of symmetry. The equations describing fundamental forces possess a beautiful, abstract symmetry called gauge invariance, which is crucial for the theory to make mathematical sense. Introducing mass the obvious way, by just adding a mass term, brutally breaks this sacred symmetry. The Stuckelberg mechanism is a workaround. It introduces a new, auxiliary field that interacts with the gauge boson in such a way that the mass appears, but the precious gauge symmetry is miraculously preserved. Think of it as a legal loophole in the laws of physics, a way to get mass without violating the fundamental rules of the universe. This idea was proposed by Ernst Stuckelberg in the 1930s, predating the Higgs mechanism by decades. For a long time, it was seen as a historical curiosity, an elegant but less essential piece of mathematics, especially after the Higgs boson was discovered. But today, the Stuckelberg field is experiencing a major revival. In the quest to extend the Standard Model, physicists are considering all possibilities. It provides a powerful tool for model building, particularly in theories involving extra dimensions or for giving mass to potential dark matter carriers. It offers a different kind of genesis for mass, one that does not rely on the spontaneous breaking of symmetry that defines the Higgs. This hidden field, a ghost in the equations from the dawn of quantum theory, reminds us that there might be more than one way to build a universe with substance, and its quiet legacy may yet hold the key to the dark sector of our cosmos. Symmetries are the hidden scaffolding of reality, but what happens when that scaffolding suddenly cracks? When a perfect, continuous symmetry of the universe breaks spontaneously, the cosmos responds not with silence, but with a new, massless particle. This is the Goldstone boson, and its emergence is one of the most elegant principles in physics. Imagine a perfectly round, smooth dinner plate resting on a needle point. It is symmetric, identical from every angle, but this balance is unstable. The slightest disturbance will send it falling, settling with its rim touching the table at one specific point. The perfect rotational symmetry is broken. The plate has chosen a direction. According to the physics, this dramatic change must produce a new, massless excitation, a ripple in the field that corresponds to rolling the plate along its rim. This ripple is the Goldstone boson, a particle born from the act of broken symmetry itself. Its defining feature is that it costs zero energy to create, a direct consequence of the symmetry that was lost. Now connect this to the most famous field of all. The Higgs field is not a single entity, but part of a more complex structure. Before the universe cooled, it possessed a certain symmetry. As the cosmos expanded and temperatures dropped, the Higgs field, like that dinner plate, fell from its high-energy, symmetric state into a stable, lower-energy state that broke the symmetry. This event should have produced several massless Goldstone bosons, so where are they? This is the brilliant twist. The W and Z bosons, the carriers of the weak nuclear force, were born massless. But as the Higgs field settled into its new state, those massless Goldstone bosons did not simply fly away, they were absorbed. The W and Z bosons, in a sense, ate them. This process gave the W and Z bosons their 3 extra degrees of freedom, the components that manifest as their immense mass. The Higgs boson we discovered is the leftover physical remnant of that entire process, the one particle that remained after the others were consumed. It is the tangible proof of a cosmic feast that gave the weak force its short range and shaped the entire structure of the atomic world. The Goldstone mechanism is the silent, universal rule, and the Higgs boson is its spectacular echo, a monument to the moment symmetry broke and our material universe was truly born. A phantom field could be the key to unlocking the universe's most fantastic shortcuts. To build a stable wormhole, a tunnel through the folded fabric of spacetime, you need more than just a gravitational warp. You need a substance that actively pushes space apart, propping the throat of the wormhole open against the relentless force of gravity that would otherwise crush it into a pinpoint. This exotic matter is described by a phantom field, a hypothetical energy field with a truly bizarre property, a negative energy density. Think of energy as something that is always positive, like the water in a glass. This phantom field would be like a glass with less than nothing in it. Its presence would create a kind of negative pressure, a repulsive gravity that counteracts the natural tendency of spacetime to collapse. This requirement comes directly from the equations of general relativity, and it leads to a profound violation of what physicists call the classical energy conditions. These are the reasonable sounding rules that matter should have positive energy and that energy should flow in a positive direction. Exotic matter, governed by the phantom field, breaks these rules spectacularly. It is the cosmic equivalent of a substance that weighs less than nothing and pushes when you try to pull it. While this sounds like pure fantasy, hints of such behavior might already exist in the quantum world. The Casimir effect, with its negative pressure between plates, demonstrates that these strange energy states are not entirely forbidden by physics. If we could somehow harness and magnify this quantum weirdness, we might one day weave a phantom field into the structure of spacetime itself. This would not just create a bridge between distant stars, it would rewrite the rules of reality, turning interstellar travel from a millennia-long voyage into a single, breathtaking step through a cosmic doorway. The phantom field represents the ultimate engineering challenge, demanding we learn to build not with steel, but with the ghostly substance of negative energy. There is a symmetry even more fundamental than rotation or reflection, a principle that the universe itself may have honored in its fiery youth. This is conformal symmetry, the idea that the laws of physics remain unchanged not just by where you are or how you are oriented, but by the very scale you choose to examine. A system with perfect conformal symmetry looks the same whether you zoom in to an infinitesimal point or zoom out to an infinite vista. There are no fundamental rulers or clocks, no absolute sense of large or small. The geometry of spacetime can bend and warp, but angles are always preserved, creating a universe of self-similarity at every conceivable level. The fields that govern such a world are known as conformal fields, and they are the mathematical heart of some of our most profound theories. In string theory, the world, sheet traced out by a vibrating string, possesses this exact symmetry, a crucial ingredient that allows the theory to produce consistent, finite answers. In statistical mechanics, the frantic dance of atoms at a critical point, like the moment water turns to steam, becomes scale invariant, with fluctuations occurring in patterns that look identical at every magnification. These are glimpses of a cosmos without scale, a perfect fractal reality, but our universe is not like this. We have atoms and galaxies, a clear hierarchy of sizes, and most importantly, we have mass. This tells us that conformal symmetry, like so many others, had to break. The generation of mass for particles like electrons and quarks, potentially even the very emergence of spacetime from a more fundamental order, could be the direct result of this symmetry breaking. As the universe cooled from its initial, featureless state, it may have undergone a phase transition where conformal symmetry was lost, introducing a fundamental scale for the first time. This single event could have frozen in the masses of particles and the very dimensions of space, creating the structured, hierarchical cosmos we call home. The search for a nearly conformal field theory, one that walks the razor's edge between scale invariance and the world we see, is a driving force in modern physics, a quest to understand the moment the universe chose its size. Our final theory asks if we have been profoundly mistaken about the most familiar force of all. What if gravity is not a fundamental interaction, but a secondary effect, an illusion that emerges from a deeper, more fundamental layer of reality? This is the radical proposal of emergent gravity, a concept that turns Einstein's cosmic trampoline on its head. Spacetime itself, the very stage upon which the universe plays out, may not be the foundation. Instead, it could be a holographic projection, a collective behavior that arises from the frantic interactions of countless quantum bits of information. The key to this emergence appears to be a phenomenon that Einstein famously called spooky action at a distance, quantum entanglement. When two particles become entangled, their fates are linked instantly, regardless of the distance between them. In the framework of emergent gravity, this spooky connection is not just a curiosity, it is the very thread that weaves the fabric of space, where there is a high degree of entanglement between the underlying quantum components. Space itself forms and connects. Where entanglement is absent, space tears apart. This suggests that the smooth, continuous geometry of general relativity is a kind of average, a large-scale approximation of a vast, invisible network of quantum connections. The most well-known version of this idea comes from physicist Eric Verland. With his theory of entropic gravity, he proposes that gravity is not a fundamental force, but an entropic force. Think of the mundane force that pushes a tangled rubber band to spontaneously untangle itself. It is not pushed by a fundamental force, but by the statistical drive toward disorder, toward higher entropy. Verland suggests gravity is similar. The apparent attraction we feel is a consequence of the natural tendency for disorder to increase. When a material body approaches another, it changes the information content, the entropy, of the underlying microscopic structure of spacetime. What we perceive as a force is really just the system rearranging itself to maximize its disorder. This emergent picture provides a stunningly elegant explanation for the universe's most puzzling ingredients. Dark matter, in this view, might not be a missing particle at all. The observed gravitational effects we attribute to invisible matter could simply be a mismatch between our fundamental understanding of gravity and its true emergent nature. The excess gravity holding galaxies together might be a natural consequence of the emergent properties of the quantum information from which space is built, no exotic particles required. Similarly, the accelerating expansion of the universe, dark energy, could be understood as an emergent effect of the changing entropy and information content of the cosmos as it evolves. This is not a small adjustment, it is a complete paradigm shift. The challenge for emergent gravity is formidable. It must reproduce all the stunningly precise successes of general relativity, from the orbit of Mercury to the bending of light around galaxies, while making new, testable predictions that differ from Einstein's theory. Current experiments, like the precise mapping of the cosmic microwave background and the observation of colliding black holes, are searching for any tiny deviation that could hint at gravity's illusory nature. If this radical idea is correct, then the force that grounds us, that guides the planets and bends the cosmos, is a cosmic mirage. We are not living in a universe with gravity, we are living within a colossal computation whose emergent properties create the beautiful and ultimately deceptive illusion of force and geometry. We have traveled from the tangible proof of the Higgs to the furthest edges of physics, where fields may encode consciousness and gravity itself might be an illusion. 30 different windows into the cosmos, and every single one reveals a universe humming with hidden activity. These are not just abstract ideas for physicists to ponder. They are the fundamental brushstrokes painting our reality, the silent symphony playing just beneath the surface of everything we see. This journey reminds us that the cosmos is far stranger, more complex, and more wonderful than our everyday senses could ever suggest. The frontier of physics is not millions of light years away. It is here, in the empty space between your hands, in the gravity that holds you to the earth, in the very flow of time you feel passing by. Each of these theories is a testament to human curiosity, a bold attempt to listen to the whispers of the universe, so keep questioning, keep looking deeper. The greatest secrets of existence are still waiting, hidden in the quiet fields that shape our world.